A general second-order linear partial differential equation can be classified using a discriminant. We write this discriminant as delta equals b squared minus ac, where a, b, and c are the coefficients on the second derivative terms of the equation. There are three cases to remember. If delta is negative, the equation is called elliptic. If delta is 0, the equation is called parabolic. If delta is positive, the equation is called hyperbolic. Let's classify our first example, Laplace's equation. This is written as u sub xx plus u sub yy equals 0. Comparing this to the general form, we identify a equals 1, b equals 0, and c equals 1. Now we compute the discriminant, delta equals b squared minus ac, which is 0 squared minus 1 times 1, giving 0 minus 1, which equals negative 1. Since delta is negative 1 and negative 1 is less than 0, Laplace's equation is elliptic. As a check, this matches what we expect, since Laplace's equation describes smooth, steady-state behavior, which is the hallmark of elliptic equations. Next, let's classify the heat equation. This is written as u sub t equals alpha times u sub xx. Here we match t to the role of x and x to the role of y from the general form. This gives a equals 0, b equals 0, and c equals negative alpha. Now we compute the discriminant. Delta equals b squared minus ac, which is 0 squared minus 0 times negative alpha, giving 0 minus 0, which equals 0. Since delta equals 0, the heat equation is parabolic. As a check, this matches expectations, since the heat equation models diffusion over time, which is the classic parabolic behavior. Finally, let's classify the wave equation. This is written as u sub tt equals c squared times u sub xx. Comparing to the general form and computing the discriminant, we get delta equals c squared. Since c squared is always positive, delta is positive, so the wave equation is hyperbolic. As a check, this matches expectations, since the wave equation describes oscillations that travel, which is the defining feature of hyperbolic equations.